Welcome back to Physical Chemistry. Today we're carrying on the interaction between light, visible and ultraviolet light, and molecules. And now we're looking more at the energy levels and just drawing them in a slightly different way. Last time we were looking at orbitals, and this time we're looking at the energy levels and comparing the energy levels of vibration, which would be these ones in here, and the energy levels of electronic energy levels. So imagining we have what we had last time, where we took a double bond and we excite one of the electrons from the bonding state into the antibonding state. What do we expect to happen? Well, we imagine that when we excite the electron into the antibonding state, that the two atoms will become less well attracted to each other, and so the average distance between them in this weaker bonding state will be longer. We would also imagine that the energy well that we would see is not as deep, and it's higher in energy compared to the starting state. So imagining the starting state there that we had a distorted oscillator, so we've got a very high increase in potential up to the zero, because the atoms can't crash into each other and make a neutron star. And we've got very open energy on the outside, because if we rip the bond apart, then they're not going to be attached anymore. So it can't be possibly symmetrical. What we also know is that, we expect it to go up and across, and maybe get a little bit shallower as we make an excited state. So if we draw a diagram of it and simplify it a little bit so it's not got so many energy levels in between, we can see something like this, where we've got the lowest energy state here. This would be the lowest electronic energy state, with vibrational energy states in between. So effectively our molecule is vibrating between this position, this length, and this position, this length. And our excited state is up here, vibrating between this position, this length, and this position over here, this length. If we warm it up, if we give it more vibrational energy, it could be up here or up here. So we get vibrational energy states inside the electronic energy state. What's interesting about this, or very important about this, let's change colour, is that if we excite our molecule here, from somewhere in between, let's draw 3 lines up, we may not be able to get to the ground state. So if we have this molecule in the middle, it's vibrating between one end and the other, and it spends most of the time in the middle, like this. So it's the probability of finding it in the middle is way higher than the probability of finding it at either end. So if we excite this molecule from here, we can't get into this ground state, because the two atoms are not in that position. Effectively, this bond is shorter up here than it ever is in the excited state. This is related to a theory that I would like to introduce to you, called the Condon principle, but also in other ways, because it's very similar, the Born-Oppenheimer approximation. What it effectively says is that when a photon of light comes in, the molecule must react very quickly and absorb it. It has to absorb it effectively instantaneously, and that means that the atoms can't jump suddenly. The Born-Oppenheimer approximation is similar, but it's a slightly different case. So in this case, what we've got is an atom at 0 and another atom which is oscillating between these 2 points. And if we choose it at the middle point and excite it one electronic state, it can't get into the ground state, so it typically will go into some excited state. I've only drawn 2 states in here. So it will go up into the blue one, like that. That would be the most likely thing to happen. Because it's a vibrational excited state, it can hit other molecules, and so it can get down into the ground state. Vibrational de-excitation can happen crosswards because it's the molecules hitting each other, so they can go down across. So we've got a vertical transition, which is caused by light on this particular diagram, and we've got a diagonal transition, which is caused by thermal relaxation, caused by collision with other things. Then this molecule in the ground state would like to go back down again, but it can't get down into the ground state either, so it typically will drop into the excited state. I've not drawn it perfectly, but getting down into this state is also unlikely because the molecule is at its extreme stretched end at that point, and so that's very low probability to happen, but it can get into this excited state. In a real model, there would be a lot more vibrational excited states in between, and it's typically the second-ish excited state that the molecule will go into, and it's typically the second-ish one that it goes down to. So this, let me get rid of this line because this line is doing nothing, and this bit of line because it's also doing nothing. So our excitation is from the middle here up to the top, and from the middle here down to somewhere where it overlaps, which is typically an excited state. So we can see that the way up and the way down are not the same, and we are getting some kind of thermal energy out each time from this transition. This could be a light emission from the excited state down to the ground state again. And we can see that we've converted blue light into not quite so blue light, into redder light. That would be our total transformation. We've devalued our light by passing it through our molecule, by absorbing it and re-emitting it. This is useful because it means that we've got some kind of emission, and so we can look at a new type of spectroscopy, not only absorbance, but also some kind of emission spectroscopy. This effect is called fluorescence, and I can show it to you here on this piece of paper. So this is a piece of paper with fluorescent marker on it, and if I bring up a light close to it, you can see it appears to glow, and that's because it's absorbing the blue light and giving out a sort of yellow or greenish light. I have a slightly better version here. This is an orange dye, and if I shine my ultraviolet light on it, it looks yellow. It's a bit difficult for the camera to get that. Let's try it with this one. This is a yellow one, and it also looks yellow. Ah, that's good. So that looks brighter yellow. The camera is actually better at picking up the ultraviolet than my eyes are, so it doesn't look so bright to me as it does to you. This dot behind it, I can't see it quite as much as you can. It's unfortunate that cameras pick up that better. Now, you might have noticed that this particular sample doesn't stop glowing afterwards, and so there is a problem. This is obviously not this process. Something different is happening. We can look at that in a moment. This other one is also the same, so if I take my orange one and I give it a good charge with the light, it then appears to be yellow and glowy. And on the other side, where it didn't get so much light, it's orange. It'll last a few minutes. It's kind of sand, so I can mix it up and give it another charge up. With the light, it's very much the same principle. as any other light charging material, like the like children's ornaments. What you can also notice is clothing is often very extremely coloured. If you shine an ultraviolet light on it, bring it over to the curtain here, or me. To describe phosphorescence, the thing that causes this letter from my children to stay alight for a little while, we will need to simplify the diagram a little bit. So first of all, we'll look at the same diagram that we've got and think about fluorescence, which is the magic marker, the highlighter pen, and that doesn't charge up and stay coloured. It goes away immediately, so there's obviously a completely different time scale where fluorescence occurs and where phosphorescence occurs. So I've redrawn my drawing, and we'll have another look at it over here. Got lots of lines on it, so we'll try to go through this a little bit slower, make sure that everything gets understood as much as possible, at least by me. So we take this black line, will be the first excitation from the ground state, the zero state of this zero state. This is the zero state of the electronic state, and this is the zero state of the vibrational states. And we can go up, but we can't hit any of these excited states until we get to this second excited state. In this case, I think I've drawn it a bit wonky, but in the second excited state, we could obviously go up to the third excited state, and we would come in a little bit inside. Then it can drop down through these states, and it would typically go right down to the ground state, and then it will try to drop from there, the center of that, down to the lowest one that it can get to. It can't get to this one because it's not inside, so it will come down also to the third or the second excited state. So that's not the only thing that can happen, however. We could have some molecules that are already in the first excited state, and they might be able to get into a lower energy state when they go up. And we might have some that don't come down, that drop down immediately, and they could drop down into the end of the lower excited state as well. So sometimes the transition is in both. Let's have that one. Sometimes the transition is in both. This is possible because although it's not right on the peak, there's quite a lot of probability there. The molecule spends a reasonable amount of time here. It doesn't spend very much time at the ends, and it can get down to any state where that position is included. If we consider these to be possible colours, and we can see that there are a range of different colours in the excitation, and there are a range of different colours in the emission, and they all have the same physics. It is a transition from around about the middle to somewhere near the end of the shape. And because these two shapes are similar, the bottom of the shape is quite similar, then we will expect to see some similarities between the absorption and the fluorescence spectra, the absorption and the emission. Added to this is, of course, all the other effects that we possibly might have. So we might see some kind of distortion from the Doppler effect if our molecule is moving towards us or away from us, which is particularly apparent in the gas phase, obviously, less apparent in the liquid phase, and almost not present in the solid phase. And then we can have effects of other bonds nearby, distorting it or pushing electrons in or taking electrons out, which we will cover in organic chemistry. So to improve the clarity of my diagram, I'm going to go to a slightly simpler form where the shape of the curve is not shown, where we've just got a stack of energy levels, and that enables us to put more curves into our diagram without getting confused. It's just a way of simplifying it, and it's a special type of diagram. You can look it up. It's called the Jablonski Diagram, which sounds humorous to some people. It's somebody's name. So going back to our diagram, hang on, got to do that. Going back to our diagram, we've now got a new diagram without the curve shapes. If we draw on our transitions from before, they would be this one here, but we haven't got the shape of the curve to define why it goes from the 0 to the second energy state. Oops. And then we have the back one, which was this one. There were others, but we'll just leave those on for clarity. So we'll have a little decay from there to there. It's got a wiggly line on it. I think you can see that. It's got a little wiggly line on it, and that denotes that it is not radiative. So we've got this absorption, and we've got this emission. That would be our fluorescence. Now we want to define the phosphorescence, so we have to go over to the other side of the board where we see a new thing. So this is the effect that we saw with oxygen. So we've got either our two electrons in opposite directions, the ones in the outside of the molecule, or we have them unpaired. If we put this molecule then into a magnetic field, we will split the energy into different levels, but this one is not magnetic, so it only has one state. It doesn't matter which angle it's in, it has one state, and so that's typically called the S state, the singlet state. So this would be S0 and this would be S1, where we've got an electron and excited it. If we flip an electron over, so this one, and flip the spin over, that transitions to another state, which is called the triplet state, because quantum mechanics is weird. It has three possibilities, three possible energy states in a magnetic field. Let me rub a little bit of this out so I can do it. And this would typically be over here, or typically be drawn over here. And that also has vibrational energy states. So let's have two of them. Whoops, these are getting closer together, so that's bad. They should get closer together towards the top. So this is T1 and this is T0. So what we can have is we can have transition from our singlet state here across into the triplet state. Let's have it go, let's have it go across there. And then we can have it go down, and this would be our emission. And it also has to get back somehow. This could also be an emission state. The vertical transitions are quantum mechanically allowed because we are taking in a light photon or giving out a light photon, whether we're up or down, and exciting the energy. The diagonal transitions they happen, but they're quantum mechanically called not allowed, which means that they're comparatively rare. It's why you have to shine a lot of light onto these light storage devices for them to absorb much. And the vertical one here is also allowed, so it can go down to here, but now it's stuck and it can't get back to the singlet state without flipping an electron over. I should have drawn them higher up. Let's put it to T0, maybe up here, to make it simpler. So we've had the theme that we can have different triplet energy states and they can change energy or whichever. Let's come down to this one. The emission here is also radiative, and this would be phosphorescence. And the time scale of these two processes is much longer than the time scale of this process, because this can just happen immediately, so it's very, very short. That's why our fluorescence is only apparent while our light is actually on it, and this is a slower process, and it's of the order of it's fractions of a second. So the triplet state can last some time. Some of the better ones last hours, but it's not their half-life. But the apparent time that they can be visible for is hours. The flipping of an electron quantum mechanically requires a unit of spin, and because a photon contains not very much spin, it is actually spinning, but it doesn't have very much momentum. It can't flip over an electron, so it doesn't have the rotational angular momentum to flip an electron over, and so this is not allowed. We can't go from here to here directly. At least it's rare. This transition is usually requires interaction between the spin of the electron and a large orbital. So a big orbital like an F orbital, an outside orbital. And so we would typically see this transition happen if we have heavy atoms in our system. So if we have got only organic compounds, it doesn't happen so much. But some big compounds with heavy atoms on, chlorine atoms for example, are very good at flipping an electron over and going into the other mode. The shape of these energy wells, and the reason that this one is going from the ground state to the top, is similar, but obviously to draw all three of those things onto one diagram would make it even more impossible than it already looks. With just these two things on it, it's already pretty awful. While we've got this diagram, however, we can also show one more thing, but I'll get rid of this triplet state to make the diagram a little bit simpler first. Okay, we're back. Same diagram, different phenomenon. If we excite our electron, effectively, into a state in the middle here, it has a new problem. First of all, it's quantum mechanically not allowed because there's no energy state for it to go into. But if we have a lot of light, it could jump up there and then fall back down again immediately. This is all okay. We would typically send it all the way back, and we would call that scattering. So the light comes in, it hits something, it's absorbed, it's immediately re-emitted. So we put our photon in, and the photon comes back out again. The important thing about this is the photon that comes out, although the time is the same, it's not delayed, it is not going in the same direction as the photon that came in. So we can imagine this as being physically identical to scattering. It's absorbed and re-emitted immediately. So we don't just scatter off very fine surfaces, we can also scatter off molecules. But in this case, it's being absorbed and re-emitted. However, in a very low amount of time, in a very low proportion of cases, it's better, the molecule doesn't go back into the ground state. So we've excited it to here, and it drops back down into an excited state instead, a vibrationally excited state. Now, just like fluorescence, we've changed the color of our photon. We've shifted it down in energy, and we've got redder light than we had before. Typically this would be colored light, visible light, or ultraviolet, and now we've got redder light than we had before. It's not shifted by very much because it's an infrared transition, but we've got a different color. It's not as bright as fluorescence, so we can't use it in the same way. We can't measure it quite so easily. It's about 1 in a million photons. So 1 in 10 to the 12 photons will do this. Depending on other things that we can do, we can increase that by several factors, several powers of 10, but it's still a very minor number of the number of photons. It's a low probability event because it's quantum mechanically not allowed. However, it's very useful because if we can block all the light of the wavelength that we put in, we can measure the color of the light that comes out, and we get out the energy of this transition, which is to say, it's a very similar technique to the X-ray techniques that we were looking at before, that we have a difference between two states that tells us really this energy level. We are actually measuring a roundabout path, and what we get is this difference. That's very useful. It's effectively the same as an infrared measurement because we're getting vibrational information, but the quantum mechanics is different because we have a completely different selection rule. So quickly, to make sure that it all works, the selection rule is which light is preferentially, which transitions occur preferentially. So if we have this, we're seeing light out. This is called Raman Spectroscopy. It's a person's name as well, and I'm probably mangling it as well. So sorry about that. But this is a type of spectroscopy named after a person. And instead of infrared, where the transition has to cause a change in dipole moment, in this, our transition, the hidden transition here, has to cause a change in polarizability. What that means is that if we have a molecule like this, CH4, so let's make our hydrogens out here. So if we have a molecule like this, and we notice that it's not infrared active, it is infrared active, but not very much, because these are not very polar bonds, so we don't see very much. This transition, where they all go out and in, is very infrared inactive, because it doesn't have any dipole at all. If we do just a single one, so just two of them, then we can see it, because then we're changing the polarizability of the molecule slightly by changing the length of this bond, so it is infrared active. But all four of them going out and in at the same time in a sort of, don't know what to call that, squeezing mode. This particular mode is called breathing, actually. So this would be a breathing mode, and it would be not infrared active. We wouldn't see it at all. This would be exactly the one that is Raman active, because it's getting bigger and smaller, and the polarizability is dependent, of the molecule is dependent on its size. What's more interesting for us, biomaterials people, is that water has a very strong dipole moment, this way, and most of its infrared transitions are, or most of its vibrational transitions are infrared active. So if we have one going, so if we have our hydrogen going out and in, if we have both of our hydrogens going out and in, and even if we have scissoring, bending movements, they are all infrared active. We get a lot of bands, and it's very, very, very intense, meaning that if we try to measure infrared in water, we tend to not measure anything. Most of the light gets absorbed by the water. However, most of those are not Raman active. There is a Raman active Raman active vibration. It's where they both get longer, where the molecule gets bigger. That is a Raman active transition, that's what I wanted to say. But all of the others are only infrared active, which is important. Unfortunately, due to symmetry, some molecules, some transitions are both, and some molecules, some transitions are neither. That's just how it is. But the spectrum and the interactions are usually very similar. A lot of the spectra look similar, just the relative heights of the different peaks are very different, because the ones that are allowed, quantum mechanically allowed, so very strong, are different in infrared to in Raman. And as I said, it's very good for biological measurements because you can see through water. Water has a single peak and it's relatively sharp, so you can see next to it. Whereas in infrared, it's got a broad band and is quite black. Okay, I think that will do for this time. I'll have to cut this and put it onto YouTube so that you can see it, and then we will take it from there. So see you next time.